Hello and welcome to the National Weather Service Chicago office. It is certainly our pleasure to have you here today for our open house. This little intro tutorial will talk to you about, first, Doppler radar, and I'm sure most of you saw that on your way in. That was the giant golf ball or volleyball or soccer ball looking thing on the pedestal, depending on your favorite sport. And we'll also talk about warning issuance, which is the #1 priority of the National Weather Service. Now the Doppler radar, inside that white shell is a rotating dish, like many other radars out there. This dish can scan in different strategies depending on what NWS meteorologists want. When there are a lot of storms out there, we will scan quickly in many angles to determine the structure of these storms. This is a graphic showing when the radar is scanning at a very high rate of speed in many angles. Here is color coding one of the lowest angles that the radar would scan, and you notice as you get further from the radar, the beam becomes higher and higher up, and that's basically because the Earth curves away from a single point, like the radar here in Romeoville. After the radar is done scanning and rotating around one angle, it will pivot upwards. The different colors here reflect different scanning strategies, basically, that the radar is doing. It is determining target information, such as location, first, and then determining the velocity and speed at which it is moving. Basically, it's doing that in the green scans, a little bit less of that in the blue scans, and the red scans, it's basically only determining location. When the energy is reflected back to the radar, a receiver takes the information in, and then it is processed by powerful computers and outputted in a format that NWS meteorologists can recognize and make decisions based upon. Doppler radars are basically co-located at each National Weather Service forecast office, though there are a few other radars between offices to help complete coverage across the United States. There are over 120 radars across the nation. Here is a look at a radar image that probably you're familiar with, seeing on TV or on your mobile device or on the internet, and this is called reflectivity, or basically power that's reflected back to the radar. It is saying how heavy the precipitation is and often how concentrated it is. The warmer the colors on many color scales, including this one, yellows, oranges, reds, would indicate heavier precipitation. In this color scale, the yellows, pinks, or higher dBz, decibels as we say, indicate likely some hail within some of these thunderstorms. When we put these images together, we can make a loop and basically see storm trends with time. Changes in structure and changes in shape of the storms tell NWS meteorologists a lot. So here's a loop of storms that are crossing Cook County and into northwest Indiana from just last week. Now we call this a Doppler radar, and why we do that is because it can measure the Doppler effect. In other words, it can measure the phase shift of the particles that reflect energy back to the radar. From that phase shift, the radar can determine what way the particles are moving and just how quickly. And that's shown in this image here. Greens basically indicate where motion is towards the radar here in Romeoville, while reds indicate where the motion is away. So for instance, in this thunderstorm activity in Cook County in this example, we see motion towards and then motion away, basically divergence, and that could indicate that the storm is putting out a strong downdraft. This is how radar can also see rotation. When we have strong speeds towards and away from the radar right next to each other, can infer rotation at times, and that can be the beginning signs of possibly a wall cloud and maybe even a tornado. Again, this is all relative to the radar here in Romeoville. By putting the imagery together at all the angles, we can basically see a 3D structure of the storms, and here is an example of that over time. This particular example showed a storm quickly develop upwards and then even more quickly descend and produced an over 60-mile-per-hour wind gust at Aurora Airport in Sugar Grove. Now in 2011 we had the biggest advancement to Doppler radar since it was installed in the early 90s, and that was the transition to dual polarization. Basically, the electromagnetic pulses that are sent out are done both in a horizontal and vertical manner now. This gives us more information on the precipitation concentration, makeup, and size of the particles. From that, in this example here in northwest Indiana, we can watch here, and this is called the correlation coefficient. And notice how all the oranges and reds change to purple. Basically, that's saying this mixture is becoming much more homogeneous. And what we're seeing is rain and snow changing to all snow. Radar can also estimate precipitation. Here's an example from just last week. Heavy precipitation analyzed from Chicago through northwest Indiana. Doppler radar can also see non-meteorological elements. In this early morning case, when an inversion was present, the radar beam was refracted back down to the ground. The Doppler here indicates very high speeds in these yellow circles. Notice how they correlate to interstates. We were kind of playing police here that morning because we could see the speeds of vehicles on the interstates. It's not that odd of a phenomena that we can do that in the mornings, but it's because the radar beam is refracted back down to the ground. Now you may ask yourself, boy, that would be a problem during thunderstorm days, but on most thunderstorm days there's not a strong inversion low to the ground. Now, warning issuance. Again, this is the #1 mission of the NWS because it goes toward protecting life and property from dangerous weather. The decision to issue a warning by an NWS meteorologist is based on sort of three things: what the radar is showing, what the environment is capable of that day, and what our eyes and ears in the field are telling us, basically our sky-warned storm spotters. When the decision is made to issue a warning, we must do it efficiently and accurately. And we go about that through a program called WarnGen. Here's an example of what that program looks like. Basically, we put a cursor on a storm, we give it a motion that we feel that it's going to move, and some storms don't always extrapolate. Mother Nature can throw a wrench in there and turn things to the right or left, and meteorologists have ways to identify when that could happen. And we draw an area that we want the warning for. We select what type of warning here over in this interface, and then we see the many options that we can select in blue here for what we want to say that the storm is capable of. Wind, hail, tornadoes. We can mention key outdoor venues, like baseball parks, for instance. We can mention interstate mile markers for those traveling, and other call to actions that we'd like people to take. Where to find this information? On our website, weather.gov/Chicago, or our mobile website, mobile.weather.gov. Here's an example on our webpage. You can find warnings on the map by clicking these links here, and radars below with a thumbnail image, or on the left-hand blue column. Thank you again for visiting the National Weather Service today on our open house, and we hope you have a wonderful experience.